This is 40 Days of Chemistry, part 22. This time looking at 9.6.2 steels and rusting. And the first thing to look at is active versus passive metals. Active and passive metals are both reactive metals. They react with oxygen or chemicals in the environment to produce a corrosion product layer. But for active metals, the corrosion products offer no protection from further corrosion. That's because they're porous or not tightly bound. Therefore, oxidants and electrolytes can still contact the metal surface. Therefore, they can keep corroding. An example of that is iron. Passivating metals, though, the corrosion product is inert, tightly bound, impervious and self-repairing. Therefore, the corrosion product forms a barrier against further corrosion because the oxidant and electrolyte cannot contact the metal. An example of that is aluminium, which forms an aluminium oxide layer. Chromium is also passivating as well. There are some metals called noble metals, and they're unreactive metals. They don't react at all. Therefore, they're not considered passivating because they don't form a passivating layer. Things like tin, silver, platinum and gold, for example, are not considered passivating even though they don't react. Iron alloys, shipping and rusting. We know that iron alloys, i.e. steels, are the main metal used to make ships. That's because they've got high strength and stiffness, and they've got very high strength per dollar as well, or high strength per weight value is very important, and they're readily formed and welded. But because it's an active metal, it rusts, and therefore protection is needed. But before we look at rusting protection, we've got to look at rusting itself. And there's 5 main stages of rusting. First of all, when in contact with oxygenated water, some oxygen will always be reduced at some sort of carbon impurity where the oxygen concentration is high. That's called the cathode. At a site of stress, which is distant from the high oxygen concentration, it's going to form the anode, and that means iron is going to be oxidized there. There's electron transport through the steel from anode to cathode sites. There's also ion transport through the water or electrolyte layer on the surface, with anions going to the anode and cations going to the cathode. That means the iron 2 plus ions and the hydroxide ions meet, and they form a precipitate of iron 2 hydroxide, and that then oxidizes to form the common product known as rust, or hydrated iron 3 oxide. So what factors affect rusting? Well, rusting is a galvanic process. You need the iron, which is going to be the species that's oxidized. You need the oxygen, which is the oxidant. You need water, which is, in case, the electrolyte. And any factors that promote ion transport, electron transport, or the oxidation reduction processes will promote rusting. And so here are the things that do actually accelerate the rusting. First of all, high oxygen content, because that means you've got more oxidant there, more oxygen. High ion concentration in the electrolyte, which means you've got faster ion transport. Increasing amounts of carbon in the steel increase the number of cathode sites, therefore increase the rate of rusting. If you've got sites of stress, that means the iron is oxidized more readily, which increases rusting. If you've got galvanic contact with a less reactive metal, that makes iron the anode, and therefore increases the rate of oxidation, and therefore increases the rate of rusting. High temperatures increase reaction rates, therefore it can increase the rate of rusting. Low pH, which means acidic conditions. Oxygen is a stronger oxidant in acidic conditions, and hydrogen ions oxidize metals, so therefore low pH accelerates rusting or accelerates corrosion, because at very low pHs you don't get rust forming because it can't form in those low pHs, but you do get oxidation of iron. And finally, differential aeration or crevice corrosion. Areas of low oxygen become more inertic and therefore accelerate the rate of rusting in those places. Now we're going to look at different types of steel, and the first steel we looked at was carbon steel. Now, carbon steel is an alloy of iron and about 0.05 to 2.1% carbon. Anything above that 2.1% is called cast iron or wrought iron, so be aware of that. 2.1% is the maximum as far as carbon concentration is concerned. Steel, all types of steel, I think is greater than 0.002%, but specifically carbon steel is between 0.05 and 2.1% carbon. As you increase the carbon concentration, it becomes stronger and harder, which is very important. But there's a trade-off, because as you increase the strength and hardness, it becomes more brittle or less ductile, and the corrosion resistance decreases or the corrosion rates increase. What else can carbon steel contain? Carbon steel can still contain these alloying elements and still be called carbon steel. It contains 1.65% manganese for hardening and toughening, 0.6% silicon, which is used to remove oxygen in the steel making process, but it also hardens the steel, and 0.6% copper, which adds hardness and also adds corrosion resistance. There's a lot of different grades of carbon steel, but the 3 main ones are low carbon steel, 0.05 to 0.3% carbon. It's strong, but it's also malleable because of its low carbon content. It's used for things like car bodies and nails, things that have to be formed into shape. Mid-range or middle carbon steel can be 0.3 to 0.6% carbon. It's harder and stronger, so it's got a higher carbon content, and it's used for automotive parts and structural parts. And then you've got very high carbon or high carbon steel, which is 0.6% carbon plus. It's very hard because of the high carbon content, used for cutting tools such as knives and scissors, and also used for springs. Now, when carbon is added to steel, some of the carbon can sit between the iron atoms in a phase called ferrite. That's basically like pure iron, which is this over here, 0.02% carbon. The carbon will just sit between the iron atoms, and it basically just looks like pure iron, except you've got a bit of carbon in there. But if you add more than that, some of the carbon actually reacts with the iron to produce a hard brittle compound called cementite, and that forms in layers inside the iron grains, and it's called pearlite when you've got these layers of iron carbide or cementite, and that makes the steel much harder but it also reduces the ductility because this phase is quite brittle. When you get to 0.8% carbon, pretty much all the grains now are these perlite grains, which you've got alternate layers of iron with cementite in between. Anything more than 0.8%, you start getting regions inside the steel where you just actually get big chunks of cementite. Now they're quite hard, which makes the steel very hard. It also makes the steel brittle. So that's why increasing the carbon content makes steel harder but more brittle. Which is important when we start thinking about HSLA steel. Now high strength low alloy steel, or HSLA steel, is steels designed to have high strength, toughness and some corrosion resistance. They're used in construction, for bridges, roller coasters, etc., where strength to weight ratio and fracture resistance is vital. They've got low carbon to make it low, have a low corrosion but also be tough. You want low amounts of oxygen, sulfur and phosphorus, as these make the steel brittle. You want manganese about 1.5% to remove oxygen and sulfur and also increase hardness and toughness. And they're these small percent of alloying elements. And just some examples are titanium, vanadium, niobium, zirconium. There are many more they can add. But these elements combine with carbon to make carbide precipitates. And these carbide precipitates, first of all, prevent that brittle cementite formation. They prevent that iron carbide formation, which keeps the steel tough. You've got no carbon impurity sites because they actually soak up and react with all the carbon, which lowers corrosion rates. And the precipitates keep the iron grain size small. And I've tried to draw a very small grain iron here compared to the previous page, and that makes it very strong. So the fact you've got these carbides in there, it takes away carbon, which increases corrosion resistance. You've got not big chunks of brittle cementite, which makes it tougher, and you've got small grain size, which makes it strong, which is why they use HSLA steels for those particular applications we talked about. And finally, stainless steel. Stainless steel has been alloyed to become passivating or have very little corrosion. It's got very low carbon content to reduce corrosion rate, but it's got a high chromium content of 13 to 26% because that'll let it form a chromium oxide passivating layer on the surface. And being a passivating layer, we know it's inert, tightly bound, impervious and self-repairing, so it's a barrier to corrosion, hence stainless steel. You have sufficient nickel in there to maintain a tough crystal structure, and you have molybdenum to increase resistance to pitting corrosion due to chloride ions, and it also increases resistance to crevice corrosion. Just be aware that stainless steel won't self-repair in low oxygen environments because there's no oxygen there to reform the passivating layer. Rusting experiments. We did a whole lot of experiments on rusting. In all of them, the dependent variable was the rate of oxidation or corrosion or rusting of the steel. We measured it quantitatively by weighing the samples before and after and finding the mass difference, and the mass difference was related to the rate of corrosion. We also qualitatively measured it by looking at the first sign of corrosion, how long did the first sign of corrosion, and also a ranking system at the end of which one was more corroded to least corroded. Independent variable looked at alloying, whether we use carbon and chromium, oxygen content, salt in the electrolyte, temperature, pH, the coating, scratched and unscratched, galvanic contact, and we also compared to different metals. We had a whole range of independent variables. Control variables. In every experiment we tested one independent variable. That means everything else in this list had to be kept the same, but also the sample size, shape and stress had to be kept the same, volume of electrolyte, surface condition. So in all samples we cleaned and sanded them and dried them before the experiment, so there was no influence from surface impurities or surface corrosion. Remember, for all experiments, validity means you have controls variables, reliability means you repeat it with consistency, and accuracy means you use correct or precise individual measurements. So that's the end of that one, and there's a few more to go. Will be done by request.